Today we are going to discuss about metric topology. First, I would like to recall the definition of metric which I have given in the first lecture in the beginning of topology. So here I would like to recall the definition of metric. Metric topology. Definition. A metric D on a non-empty set X is a function D from X cross X to R which satisfies the following properties. Number 1, dxy is greater than equal to 0 and dxy is equal to 0 even only if x is equal to 1. 2, dxy dyx. Okay. Number 3, dxy is less than equal to dx z plus dz, where d is the distance function, that is distance between x and y is always greater than equal to 0. This is non-negativity and this dxy equal to 0 if and only if x is equal to y. dxy is equal to dyx, that is distance between x and y is equal to distance between y and x. This is symmetry. Distance between x, y is less than equal to distance between x, z plus distance between z, y. This is called triangular inequality. Next definition, that is definition of epsilon ball. Epsilon ball for a given epsilon greater than 0, the set B dx epsilon collection of y such that distance between x, y is less than epsilon is full epsilon ball center at x. Okay, we usually omit this d and represent epsilon ball by this bx epsilon. Okay, and this is nothing but the open sphere. This is nothing but the open sphere in metric space. Okay, here in topology we call this as epsilon ball, that is B is the epsilon ball with center at x. Okay, next I am going to discuss with you the definition of basis. As basis is not included in the syllabus, I am not going to the details of basis, but I would like to mention the definition of basis here. So next is definition of basis. Let X be a topological space in of Ts, then M B is the collection curl B is the collection of subsets of X, then B is said to be basis, then B is said to be basis, B is said to be basis for topology, topology on X if number 1 for X belongs to X, their axis for X belongs to X, their axis some basis element B1 belongs to B such that X belongs to B1. Okay. Number 2, if X belongs to B1 intersection B2, then their axis, so that X belongs to B1 intersection B2, then their axis some basis element B3, basis element B3 belongs to B such that X belongs to B3 and B3 is containing B1 intersection B2. If you draw the figure, the first condition applies for any X, and you always get some B1 that contains my X. Next, if X belongs to B1 intersection B2, B1 intersection B2, X is here, then I will always get a basis element B3 that contains X and contain in this intersection. Okay, then this collection will be basis. Next is definition of metric topology. Definition: for a metric D on a set X, the collection of all epsilon ball with center at X belongs to X and epsilon greater than 0 forms a basis for topology on X induced by D. For a metric D on a set X, the collection of all epsilon ball center at X belongs to X and epsilon greater than 0 form a basis. Okay, I have already given the definition of basis for the topology on X induced by D, and this topology is known as metric topology. Next is the definition of metrizable space. A topological space X is said to be metrizable, 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 metrizable space, metrizable space if there exists a metric T which induces, induces topology on topology on X. A topological space X is said to be metrizable if there exists a metric T that induces topology on X. Thus, a metric space is called metrizable space. Is called metrizable space. Metrizable space. Metrizable space together with a specific metric space X. Okay, together with specific matrix, specific matrix, specific matrix that metric D that induces topology on induces topology on X. Okay, topology on X. A metric space is also metrizable space together with specific metric D. Together with it, specific metric D that induces topology on X. With that, I would like to conclude. Remaining will be in the next